we present computational phase-modulated eyeglasses. The speaker is Yuta Ito, and this is joint work with Tobias Langlotz, Stephanie Zollman, Daisuke Iwai, Kiyoshi Kiyokawa, and Toshiyuki Amano. So our system, briefly described in this figure, we present a smart eyeglasses which can be reconfigurable and dynamically programmable. So before we go into the detail of our system, we briefly look through the related works. So the related area of this work is human augmentation, where people aim to enhance or assist human capabilities. And especially we are focusing on our human visual capability, like eyesight. So we're gonna briefly discuss about this current situation in this kind of field. So there is actually interesting fact that social impact of eye refraction anomalies. Like me, nearsighted people or farsighted people, if you typically get elderly, and then there is a certain economical cost for myopia, for example. And it's quite huge, like 45 billions per year in worldwide. And the fact tells that the percentage of like myopia is of course increasing. And this is kind of drastic statistics because it was used to be 25%, like 70s, and then already in 2000, they already got like 41% in US. In 15th century, there are already this kind of like art that describing already a priest probably is wearing an canonical or a traditional eyeglasses. And nowadays, like 2018, there is already a commercial product which allows you to electrically change the like near sight and the far sight glasses. So this is not like progressive eyeglasses, but more like it's switchable eyeglass. And if you look at some research area, there are people already implemented kind of static smart eyeglasses with fixed optical components, like this vision multiplexing paper. They basically combine those zoom lenses so that a person suffers some problem at the center of the field of view, for example, can also utilize the peripheral vision by using those zoom lenses. This is kind of interesting work, right? And recent years, we also got the dynamic smart eyeglasses. For example, this work presented at the SIGGRAPH, I think, demonstrated at SIGGRAPH, and then also they had paper now, a varifocal lens system which can dynamically control the diopter of the eyeglasses, because these are consisting of liquid crystal electrical tunable lenses, so you can dynamically actually change the focal length. There are, we see potentials of smart eyeglasses. If we have such kind of like programmable, flexible eyeglasses, perhaps it improves our quality of life, because you don't want to always switch different eyeglasses depending on what you want to do, like reading books or just going outside. And maybe combined with other smart systems like SISU, like head-mounted displays, maybe you can also use it for like zooming effects, smart zooming eyeglasses, more like a science fiction. Or more practical use cases, more realistic use case would be like visual assistance for tasks that need a precision works, tasks like surgery or soldering that you really have to zoom part of the scene and so on. So these backgrounds brings us to the concept. So we want to present a programmable lens combined with a first-person camera. So this way we can dynamically tune the parameter of the eyeglasses, and based on the scene that the user is looking at. So actually there is many programmable optics, but let's say we want to have several basic functionalities like focus correction, or you have some multifocus functionalities, or pan and tilts, or more sophisticated ways like aberration correction, and like zooming or macro pictures. On all these things, actually you can implement with like a liquid crystal lens. You can do this for focus correction, or you can utilize it for zooming. And the multi-focus, there is already some intraocular diffraction lenses, which basically, once you lose your crystalline lens inside your eyeball, so doctors, they replace that lenses with these kind of special lenses. to regain their focusing functionality, at least like a near sight and far sight. And pan tilt is pretty much common, like using galvanic scanning mirrors, and aberration correction. You also have that adaptive optics. But our system we present, it's kind of cover all these functionalities, and you can switch different functionalities by just choosing what kind of lens parameters you want to show. So to go on the detail of our system, we have to first introduce the key optical devices, which is called phase-only spatial light modulator, or PSLM. So this is mere a liquid crystal mirror display. So it's tiny, like a display panel, but it works as not like ordinary display to show image, but it works as a controlling the refraction index of each pixel. So if you apply different voltage, then each pixel then changes the state of the reflection. So the light coming into this display panel gets some phase delay, or it basically reflected by the display panel. This kind of device is actually used to be used in computer-generated holograms. So basically, they are using laser beam, right? So as you can see those figures. And then in the second column, you have those input phase images, which is just like a grayscale image displayed on the display. But of course, this grayscale image will be mapped into the reflection values of each pixel. And by designing these kind of phase images, you can manipulate the incoming laser beam by using diffraction effect. That means it's just a display. So you just plug into with like HDMI cable, and then you can display whatever images you want, which means that you can actually reconfigure the display panel or lens in a way that you want to display something. For example, if you render this kind of concentric lens gradation pattern, which is repeating like centric lens circles, and then it works as actually a Fresnel lens. So the incoming light then will be focusing at some point. So this works as like a convex lens. And this is actually a video we took a shot on the display panel with white background. And then as you can see, the display panel looks as if it's like a thin glass plate which changes the shape, right? Maybe I could just replay the video again. So in this way, we can actually control the lens parameter of the display in the very simplest case. And so this is our proof of concept system with, it's actually kind of bulky one because it's a monocular, it's a benchtop system, and it's also only monocular. So basically this is kind of polarization optics, which realizes with beam splitter a see-through view of the user. So the light coming from the scene going through the display panel reflected by the PSLM, and then you get the resulting image, which is already passing through this programmable lens. So there are some examples like Varifocal lens. So this lens, you can, of course, then tune the focus point of the image. So in this video, I use a perspective camera at the fixed focal length. It's just see the scene through the system, our system, and we display different lens parameters. And then this way you can focus, you can focus the different depth point. Like between this case, like it's from 10 centimeters to like about roughly about 1 meter. And interestingly, you can also combine different lenses, right? And this is like multifocal lenses where you render 2 different lenses simultaneously. Multifocal glasses has a potential to intervene the progression of nearsightedness for children. So maybe if you have our system as like just eyeglasses form factor, maybe we can dynamically display lenses for over years, and maybe this can be useful for such kind of applications. But anyway, in this picture, as you can see, 2 objects, like one is closer, 3 objects, one is closer and the 2 are just far away, they are both now focused at the same position on the right figure, because we are rendering two lenses simultaneously. And you can also combine different lenses, because you just need to combine some two lens images. Then you can get a new lens which has which keep the functionalities. So in this case, we just rendered like a plate phase image and the spherical phase images combined. You can then realize shifting and also refocusing. And if you combine multiple PSLMs, then you can even manipulate the field of view. So you can zoom or like zoom out images like this picture. Due to our optics limitations, so the image is quite dark, but at least we could show the system works as like a zooming lens. And after we verified those basic functionalities, we also combined the scene camera so that we can implement kind of dynamic feedback of the scene camera and the dynamic lens. And this application, for example, is a very kind of a fake setup where we just keep track the position of the marker in the scene by the scene camera, and our lens just try to always focus at the same marker while it's changing the lens. So here's the image, here's the video. So user perspective camera is again fixed at the static focal position, but because of the programmable lens and the scene camera, so the user perspective camera always can see the marker sharp, because our lens system just dynamically reconfiguring it. And the second implementation, we implemented the dual foci application we showed you. And then this case again, we dynamically calculate the position of the two markers from the scene camera image. And then we dynamically reconfigure the lens parameter so that the user's view can focus two depths simultaneously. Yeah, it's a bit laggy, but it's working. And then the next example, we also consider, is it possible to stabilize our view by using the plate phase image, which is just like image shift, and like a camera, expensive camera, they have like handshaking and then the anti-handshaking thing, stabilization thing. And then we also implemented that. So in the left figure, it's just a see-through image without anything. And then the marker is just shifting along the X direction. And then once we stabilize it, we display this view shift image and then always dynamically changing the parameter. Okay, let me play again. So it's kind of unstable, but still it's somehow stabilizing it. And then we find it's very interesting application, because it's again like a dynamic feedback of the scene camera and the programmable lens. Of course, the system has many limitations. First of all, the optical quality suffers from all those physical effects, like chromatic aberration means like each different spectrum, so like color, RGB, for example, they get some different refraction effect, and then you get some blurry color breaking issue. And also the system is like a benchtop, so it's quite bulky. As summary, we presented computational phase-modulated eyeglasses. So this is like a smart eyeglass system which aims to optimize our human vision by dynamically changing the lens parameters. So the advantage of the system is that we can dynamically change different functionalities of the lenses, like focus collection or like multi-point focusing, and also zoom effect. And by combining first-person camera, it has also potential to dynamically feedback the scene, and it just adapt the human vision based on what they are seeing. And the current limitations are the form factor of the system, and also there are several optical issues. And we also need to implement stereo system, and we also need to consider the practical applications. But we believe this concept showed enough potential so that people can explore this kind of smart eyeglasses. Thank you for listening.